Welcome back. In the second part of this lecture series on electronics, we'll study about rectifiers, how they work, what are their characteristics. Rectifiers are basically devices which convert alternating current, AC, that is bidirectional currents, to unidirectional currents. What does that mean? Let's say I've got a rectifier over here. It has got some input supply. Input supply is bidirectional. That means for half of the time this has got the positive polarity and this end has got the negative polarity, and for the other half time this end becomes negative and the other end becomes positive. They keep on reversing their polarities. That's what we call as bidirectional current, and normally in normal way we simply say this alternating current. It's alternating its direction over a period of time. Now this is we should understand it, and it is not necessary that it should be sinusoidal in nature. That's the most common thing to assume, but this can be any kind of bidirectional signal over here, and if this bidirectional is converted to unidirectional current, that means only the current is allowed to flow in one direction, and the current when it was flowing in the opposite direction is restricted. That's what we call as a unidirectional current, and a rectifier is a device which converts a bidirectional current to unidirectional current. Basically, rectifiers can be classified into two categories, that is half wave rectifiers and full wave rectifiers, and then we'll go into the detail of full wave rectifier, which itself can be divided into two categories as the center type full wave rectifiers and the bridge rectifiers. What are their advantages and disadvantages over one over the other, that we'll discuss in the later part of this lecture. Let's start with what is a rectifier. We have already understood that a p-n junction diode is a unidirectional device. That means it allows the current to flow from its p side to n side, but it doesn't allow the current to flow from its n to p side. Since it's a unidirectional device, it is very easy to use it to make a rectifier. First, we'll start with half wave rectifier. Let me design its circuit diagram. A full wave rectifier, let's say I've got an input supply connected to primary of a transformer, and I've got the secondary of the transformer, and I've got a diode, a load resistance connected to it, and output is taken across this load resistance. This is output, this is load resistance RL. Now, in alternating supply, for half of the time this end will be positive and this end will be negative. Now, the diode in this case is forward biased at this instant, because P side is getting the positive polarity. Therefore, the p-n junction is forward biased and it will allow the current to flow from it. That means as the current in the input increases and then it achieves its maxima and goes down, the same thing, very analogous to it, will happen at the output. But in the next half cycle, when this end becomes negative and this end becomes positive, the diode gets reverse bias, and we know that a diode does not conduct in reverse bias, so there will be no output across the load resistance. Again, in the positive half cycle, it will start conducting. So we can draw a waveform for a half wave rectifier as I draw it. Let's say this is the input supply, this is the input AC signal, and I can just draw these lines to indicate various time intervals. So this was the time when diode was forward biased, and this was the time when diode was reverse biased, forward biased, reverse biased, forward biased, and that goes on. And the name of this rectifier as half wave rectifier is very much understandable from this diagram. This is the waveform of a half wave rectifier. Now what about its average value of this output and the RMS value of this output? We can understand the average value of a current signal as that much direct current which will send through a given circuit the same amount of charge as is sent by this signal in the same time. So let's take one complete time period For half of the time period, there was current as I is equal to I naught sine omega t. I am taking simple sinusoidal signal. I equal to I naught sine omega t. But for other half, the current was 0. How would you take the average charge sent by this signal to the load resistance? We know that current is equal to dq by dt. So if you wish to find out dq, you need to integrate it from 0 to t as I dt. What was I? I is I naught sine omega t for 0 to t by 2 plus 0 current from t by 2 to t, and you can simply write it down like this: t by 2 to t, there was 0 dt. This is the total amount of charge sent by sent by this output signal through the load resistance. So what is Q? Q is equal to I naught. The integration of sine omega t would be minus cos omega t over omega, minus cos omega t over omega from 0 to t by 2. You can simplify this: minus I naught. Omega itself is 2 pi by t into cos of 2 pi by t into t by 2 minus cos of 0. T get cancelled out, 2 get cancelled out. Cos pi is minus 1, cos 0 is 1. So minus 1, it turns out to be minus 2. Minus and minus get cancelled, and 2 and 2 get cancelled. What I get is I naught t by pi. This is the total amount of charge sent by this output signal through the load resistance. Now look at, if instead of this output had there been a DC, that means direct current, how much charge would that have sent through the same resistance? If there is a load resistance Rm and I have connected some DC supply, I vary it accordingly so that whatever current is there, I adjust that I average in such a way that this sends in same amount of charge through this load resistance in time t as was sent by the output signal which we were considering. So in this case, DC supply is constant. Let's say current versus time. So it is easy to find out the total charge. You don't need integration. That's simply area under the curve, which is current into time. So charge is basically I average into time t. By definition of average value, the charge sent by that signal which we are considering should be same as charge sent by the direct current through that same resistance in the same time. Only then it will be called the average value of that signal current. Therefore, I equate 1 and 2. I get I average into t is equal to I naught t by pi. So what you get? I average is equal to I naught by pi. So when we are getting a half wave rectification, the current being sent, the average value of current of this kind of signal is I naught by pi, where I naught is peak current in this signal. I also wish to find out the RMS value of this signal current, and then we'll see various parameters like ripple factor and efficiency of this rectifier. We'll go to that. First of all, let's also find out the RMS value of this signal. So how the RMS value of the signal is defined? RMS value of the signal is defined as that much direct current which will produce in a given resistor the same amount of heat. As is produced by this signal at the same time to the same resistor. I repeat, RMS value of this signal can be defined as that much value of direct current which will send through the given resistor, which will produce in a given resistor the same amount of heat as is produced by this signal in same time in same resistor. So let's in average value of a particular signal, what we do, we equate the charges sent through the same resistor, and in RMS value what we do, we equate the heat produced in the resistor by the two. So let's proceed with RMS value. Now, Let's proceed with it. Let's say this is the signal. This is the signal. Half wave signal. For 0 to t by 2, there was current I, which is equal to I naught sine omega t, and there was 0 current from t by 2 to t. Obviously, in this time, no heat was produced. So what is small amount of heat produced in small time t? That will be given by I square R dt. And to find out total heat, I need to integrate it from 0 to t by 2 plus t by 2 to t. Obviously, that component is 0, so I am just ignoring it right here. It will be I naught square sine square omega t R dt, and I take out I naught square common out of this integration. The remaining thing inside it is equal to 1 minus cos 2 omega t by 2 dt from 0 to t by 2. What do I need to do? This is equal to I naught square r, and we have got 1 by 2 integration dt from 0 to t by 2. This is one part of it, and then there is second part, which is 1 by 2. I can take out 1 by 2 common, so I can write it down 2 over here. It is dt minus cos 2 omega t. The integration of cos 2 omega t from 0 to t by 2. This is equal to I naught square r by 2. This integration would be t by 2 minus the integration of cos 2 omega t is sin 2 omega t by 2. So it is sin 2 omega t by 2 from 0 to t by 2. Let's further solve it out. I naught square r by 2. We have got t by 2 over here minus 1 by 2 sin 2. What is omega? Omega is 2 pi by t into t by 2 minus, it is sin 0. 2 get cancelled, t get cancelled, sin 2 pi is 0. So 0 minus 0 is 0. This component also is going to vanish. The remaining thing, what I get is I naught square r by 2 into t by 2. So it is I naught square r t by 4. This is the total heat produced by this kind of signal through this resistance R in time t. Now, what do I need to do to find out the RMS value? What will I do? Let's say I take the same resistor connected to a DC supply. Now what I do, I vary this DC current in such a way that the current is equal to I RMS, such that this current is producing through this resistor in the same time the same amount of heat as is produced by this signal. If I can equate these two equations, if I can equate the heat produced by these two circuits, what will I get? I will get the value of I RMS. So what is the heat produced by it? It is easy for DC. The current is not changing. It's simply, you don't need to integrate it. Simply multiply it is RMS square R into T. Now this is equation number 2. This was equation number 1. Equate 1 and 2. What do I get? I RMS square RT. This is equal to I naught square RT by 4. Clearly, I RMS is equal to I naught by 2. I RMS is equal to I naught by 2. For this kind of half wave rectified signal, the RMS value is half of the peak value. Once I know the average value and the peak value, now I am ready to solve for the efficiency and ripple factor of this half wave rectifier. Let's proceed with it. For half wave rectifier, I average is equal to I naught by pi and I RMS is equal to I naught by 2. Let's define a parameter called ripple factor. It's denoted by gamma. We can understand that the output of a rectifier is not purely DC. It's a kind of superposition of AC and DC parts. There is a variation in magnitude. In pure DC, you have got constant value of the current. Here you don't have constant value of current. You can think of it as if some AC component is still present at the output. But we are getting is a superposition of the AC and DC components. The ripple factor gamma is defined as how much AC component is present at the output to how much DC component is present at the output. So ripple factor is defined as the ratio of AC component to DC component present at the output of the rectifier. The definition will be same even for full wave rectifier. So we know that IRMS is equal to IDC square plus IAC square. I divide the whole equation, I square and change it like this. IAC square is equal to IRMS square minus IDC square. Little jumbling of terms, a little mathematical maneuvering. IAC square by IDC square would be equal to IRMS square by IDC square minus 1, and if I remove the squares, I'll put a square root over here. Now this thing is nothing but gamma, so this is a general expression for ripple factor of a rectifier. This is square root of, ripple factor is given as square root of ratio of square of RMS value and the square of DC value at the outputs of that signal minus 1. So let's put in these values now. DC or average value is same thing. This you may call it average or DC, it's one and the same thing. Now put in these values, I average and IRMS. We have got IRMS as I naught by 2. So IRMS square is basically I naught square by 4 divided by I average square is I naught square by pi square minus 1. You can solve it out. I naught square get cancelled and the ripple factor turns out to be 1.21 for half wave rectifier. So what we have obtained, that we tried to convert that bidirectional component to unidirectional component, AC to DC, and what we did, we got an output which was a particular kind of waveform, and then we wanted to see how much AC component is present at the output, and the ratio of AC component to DC component at output is still greater than 1. That means AC component is still more in magnitude than the DC component at output. This is not a good rectification. So, higher the value of ripple factor, poorer is the rectification. Since half wave rectifier has got gamma quite greater than 1, it is 1.21. That means a half wave rectifier is a poor rectifier. Let's find out its efficiency. How would you define the efficiency of a rectifier? Efficiency of a rectifier is defined as the DC power output. DC power output to AC power input. DC power output to AC power input, and if you want it in percentage, just multiply it with 100, no problem with that. Now, what is the DC power? It will be IDC square into RL divided by what is the AC power? AC power will be IRMS square into RL plus RF. We should understand that what we are getting, the output is being obtained at the load resistance, so we have used only RL at the output. But for input, the input energy is being spent across diode as well as the load resistance. This RF is the forward resistance of the diode. However, that's too small in comparison to load resistance. You can safely ignore this thing, and then RL and RL get cancelled out, and basically the expression for efficiency turns out to be IDC square divided by IRMS square into 100 if you wish. Let's put in these values. DC value, that is the average value, and the RMS value over here, and you find eta is equal to 0.406, or you may say 40.6%. So We have got a device, we are calling it half-wave rectifier. We made it to rectify the things, that means to reduce the AC component, and at the output the ripple factor is turning out to be greater than 1, which shows that the AC component is still more than the DC component. Further, its efficiency is also just 40.6%. That's minimal. Therefore, the conclusion can be drawn that a half-wave rectifier is a poor rectifier. Let's move on to full-wave rectifier and see what we can do with that. Now, instead of using one diode, if I use two diodes, like this. And this is called center tapping. Right from the central point of the windings of the secondary of the transformer, a contact is provided. That kind of transformer is called center tap transformer, and a rectifier made by using this center tap transformer is called center tap type full wave rectifier. Let's say I have connected load resistance over here. Initially, let's say this end is positive, this end is negative. Current just wish to go to the negative end, starting from the positive end. This diode is forward biased, this diode is reverse biased. It allows current to flow through the load resistance in this direction. But this diode does not allow the current to flow simply because this diode is reverse biased. So current starts from here, move to this point and goes to the negative end through the secondary transformer. And what will happen during the other half cycle of the input AC? This end becomes negative, this end becomes positive. The second diode starts connecting. The first diode is now reverse biased, doesn't conduct. The current will flow from positive through load resistance to the negative. In both the cases, whether the diode D1 conducts or diode D2 conducts, in both the cases, the current through the load resistance remains same. The direction of the current through load resistance remains same. This is what we call as full wave rectifier. Standard type transformer has got a property that if this voltage is V0, there will be V0 available over here and V0 will be available over here. You can obviously change the center tapping to different position, change the different voltage, but that's a normal setting. And as we derive, so first of all, let's draw the waveform. What kind of waveform will we be getting? Let's say this is the input AC signal. I simply drop these lines to define various intervals. So what happens? When D1 is conducting, D2 is not conducting. When D2 is conducting, D1 is not conducting. But finally, through the load resistance, either D1 or D2 is sending current to the load resistance. So this is the full wave rectification. How will you obtain its average value and RMS value? I leave it as an assignment for you, but I can simply write down the values. Average value or the DC value for a full wave rectifier, this kind of waveform, for this kind of waveform, it is 2I0 by pi. And RMS value is I0 by under root 2. I leave it as an assignment for you. I hope you will be able to do this thing. And you know already the expression for ripple factor and efficiency. Just put in those values, these two values, and what you will get? You will get ripple factor at 0.48 and efficiency double at 81.2%. Now that means a full wave rectifier is a better rectifier because the ripple factor is less than 1. That means the AC component at output is now less than the DC component at output. And secondly, the efficiency is also decently high at more than 80%. So full wave rectifier is obviously always used instead of half wave rectifiers. That was just for theoretical purpose to understand the concept of rectification. Otherwise, half wave rectifiers are hardly ever used. However, full wave rectification can be done using this method or using a new kind of circuit, which is what we call as bridge rectifier. I'll draw the circuit diagram for bridge wave rectifier. This is the input AC signal. This is the circuit diagram for a full wave rectifier. Let's say D1, D2, D3 and D4, 4 diodes have been used. In this case, what will happen? Let's say this side is positive, then D1 and D3 are forward biased and D2 and D3 are reverse biased. Current flow like this, starting from D1, it will go to load resistance, it will go through D3 and finally reach the negative end. When the end D2 and D4 are not connected. When this side is negative and this side is positive, what will happen? In this case, now D2 and D4 would be in conducting state and D1, D3 would be reverse bias and hence will not be conducting. The current will start from positive end, it will go to D2 through load resistance to D4 and it will reach the negative end. In both the cases, current through load resistance remained in the same direction from upward to downward direction. That means whether the positive half cycle of the input AC signal is coming or the negative half cycle of the input AC signal is coming. In both the cases, this positive half cycle and negative half cycle of input AC is coming. In both the cases, current through the load resistance remains same and the output obtained is what we see in earlier case of center tap type transformer, that is LV full wave rectifier. Every other parameter like ripple factor and efficiency, the RMS value and average value would also be same for both these two circuits. However, there is one important difference, and that's the deciding factor while deciding which out of these two should be preferred and when. That's called peak inverse voltage. That is what we call as peak inverse voltage. What is that peak inverse voltage? It is that voltage which a diode in a rectifier has to withstand when it was in non-conducting state. That means, let's say in center tap type rectifier, when this diode is conducting and this diode is not conducting. This diode is conducting, okay, forget about it. But how much reverse voltage this diode is withstanding? That is the peak inverse voltage. And what factor will it depend? If this is V0, the total voltage is 2V0 over here. The initial voltage, this end, this positive, let's say this is negative over here. Let me clean it up a bit. If this is V0 over here, the peak voltage of the input AC signal, then let's say this end is positive, this end is negative. This means that diode D1 is in conducting state, D2 is in non-conducting state. So what is happening? There is no current in this direction, in this loop. That V0 voltage, the negative is being provided to the P side and positive is being provided to N side. So this V0 voltage is reverse biasing it. But at the same time, the upper V0 voltage is also being dropped across this load resistance. Since current is flowing in this direction, this end is positive, this end is negative. This positive is available to the N side of the PN junction. This V0 voltage, which was available over here, got dropped across load resistance, and that voltage is also reverse biasing this PN junction. So how much voltage is reverse biasing this PN junction? It's 2V0. So peak inverse voltage in case of center tap type rectifier is twice of the peak voltage of input signal. Let's say if input signal has got this peak at 300 volt, the diode will have to withstand 600 volt during its non-conducting state. But for full wave rectifier, no such center tapping is available. And what happens? This PLB for full wave rectifier, full wave bridge type rectifier is still V0. That means if you give the same signal to this rectifier, the diodes which are in non-conducting state will have to withstand only voltage 300 volts rather than 600 volts as in case of center type rectifier. Now this will become crucial. Let's say I have got a diode which shows reverse breakdown at 500 volts. If I use this diode and make a center type rectifier to rectify a signal whose peak voltage is 300 volts, what will happen? This peak voltage is 300 volts, diode can withstand 500 volts, but in non-conducting state, the diode has to withstand 600 volts, which is more than its breakdown voltage. That means this diode will undergo a breakdown. Or in simple words, you will say your rectifier will get burnt out. But if that same signal is given, same diodes are used in a bridge rectifier, what will happen? The diodes will have to withstand 300 volts, but they can withstand up to 500 volts, so it will be safe. Same diode, same signal, you can use them to rectify the signal using bridge rectifier, but you cannot use them to rectify using the center type full wave rectifier. That's why when we say that in case of high amplitude AC input signals, bridge rectifiers need to be preferred. Because PIV, that's a very important parameter. PIV for full wave rectifier using center tap type transformer is twice of the peak voltage, whereas for bridge rectifier it is equal to the peak voltage of input AC signal.